Okay, now we shall continue the analysis of this MOSFET amplifier. This is the circuit what we have considered in the last video. So we have a MOSFET as an active element, and R1, R2 is used to provide the required VGS, and RD is used to get the desired VDS, so that MOSFET operates in the saturation region, and we have the amplification of the output input being amplified by AV times. Before we proceed, of course, this is the small signal model of this amplifier. So instead of simply calling it as an amplifier, so it should be given a specific name depending on where we are applying the input and where we are taking the output voltage, and with respect to what terminal we are measuring the output voltage. If you carefully see the AC small signal equivalent circuit, the input, which is V in here, will be applying, so is applied to gate, and output is measured at drain. So when I say output is measured at drain, so this is not the only point. With respect to source, I am measuring. So with respect to source, output is measured. With respect to source, the input is applied. So the common terminal between input and output signal is source. When I say common signal, this is the input to input point, and this is with respect to this source. This is the output point with respect to this source. Since source is common between input and output, this amplifier is named as common. This is named as common source amplifier. Common source amplifier. In general, it is said as CS amplifier. So why it is called as common source is the source terminal is common between input and output. So that's why this is known as CS amplifier. So instead of simply saying it as MOSFET amplifier, we can say CS, common source amplifier. Okay, this is a CS amplifier. Now I need to analyze. We know that okay, this is the actual amplifier circuit. I'll apply the input voltage. I will measure the output voltage here, or I will use this output voltage for some load. So I'll be having a load, maybe in the form of some resistor. So it will be connected to this, and of course I'll be connecting a voltage source as the input. Now, what we are supposed to analyze is how does this circuit, or what is the resistance offered by this circuit for this input signal. So now I want to know what is the input impedance of this amplifier, and if you look from this, what is the output impedance. That's what is this impedances. So I have to see what is the input impedance offered by this and what is the output impedance offered by this amplifier. Suppose if I replace this by a block diagram, if this is an amplifier, it has got two terminals and it has got two output terminals. So this is input terminal. It has got some resistance, which I say it as R in. So this is R in, the input impedance, and I have a output voltage. Now there is a amount of gain that is there. So you have AV times the input voltage, and you have a associated resistance here. So this is R out. This is AV times V in. So where is V in is, this is my V in. This is my V in. So this is the typical amplifier block diagram representation. It will going to have a R in, it will going to have a voltage gain, and it will going to have some R out. So R in is what are the impedance that is looking into the network, into the amplifier, and R out is what the impedance looking towards the output side. From the output, if I look into it, okay, what is the impedance? Okay, to find out that, so what we'll do is to find out R in, suppose if I apply some known voltage source Vx, if I can find out what is the current that is entering the amplifier without, of course, with the output open circuited. So with output as open circuit. So I can able to find out what is the input impedance. So now we see this is the input signal. So I will apply a dummy source Vx. I'll try to find out what is Ix here. So this is my AC circuit. So I will apply a source Vx. Let me find out what is the Ix that is flowing here. So this is my output. This is my output. I will open circuit this, meaning I will not connect anything more. So this load is not connected. So I'll simply open it. You can see now this is open circuit. This RD is a part of your circuit. So this is not the exact load now. The load is actually connected here. I have not connected anything here. Suppose when I connect this RL, so this is actual load. Since I not connected RL here, so this is open circuit. So what is this? This is actually R1, R2. I want to find what is Ix. So what is Ix over here? So can you see this R1, R2 are in parallel? So shall I say now Ix is equal to Vx is the voltage that is applied, and what is the resistance you have? This is actually R1 is parallel with R2. Suppose if you rewrite this expression, and of course this is open circuited. You can see this is open circuited. This is the condition what we have said here. So now shall I say this what is Vx by Ix from this? Is it not R1 parallel R2? So for this amplifier, R in is nothing but R1 R2 divided by R1 plus R2, or this is also equal to 1 over R1 plus 1 over R2 whole inverse, or you can write it as R1 inverse plus R2 inverse whole inverse. So which is nothing but Rn, So this is the Rn value. So what are the condition? So you are applying some dummy source which is a known voltage source. You are trying to find Ix. Condition is output is open circuited. So from which we will get Rin as R1 parallel R2. Similarly, I need to find what is Rout is. So we have this equivalent circuit. If you can see there, when I have this as my equivalent circuit, there is a current source and there is a associated resistance. So we know that if you have a current source, something like this, and if you have a resistor associated with this, okay, assume that this is some I1 and this is R1. So I can certainly replace this by a minus plus, and I can this will be actually equal to I1 into R1, and this is my R1. So I can replace this current source with a resistance R1 as an equivalent voltage source with a resistance R1. So what are the voltage source magnitude? It is I1 into R1. This resistance which was there in shunt will become a series resistance. So I will rewrite this circuit by replacing this current source by an equivalent voltage source. So what is this now? So I have, this is R1 parallel R2. So this is gate here, this is source here, and this I will replace it by, since it is this is now positive, this is negative. What is this? This is actually Gm into VGS multiplied by RD, and you have the resistor RD here, and you have this as your. So now to this output you are connecting a Vx. And you have to find what is Ix. So Vx by Ix happens to be your Rout, provided I make the input voltage as 0. So this input voltage is 0, meaning there should not be any influence of the input. So this is grounded here. I will make V in equals 0. This is intentionally made 0. Okay, now when V in is 0, of course this is actually VGS. Does this also become 0? When this becomes 0, how about this? Will it not be like a short circuit? Because voltage 0 is nothing but a short circuit. So then what is Ix? So then Ix is equal to Vx by Rd. Vx by Rd. So then what is Vx by Ix? Vx by X, which is nothing but R out. Is this not equal to Rd? So for this CS amplifier, having this as your circuit, the R out is Rd. R out is Rd. So in this circuit, whatever we represented this by this equivalent circuit, so now this Rin is actually R1 parallel R2. This AV is GM into RD, and this R out is RD. R out is RD. Of course, in this case AV, this actually minus plus, because that's what is it's minus GM into RD. Instead of writing minus here, I'm just changing the polarity here itself. Suppose if you write the polarity plus minus like this, then it is minus GM into RD. Okay, this is what is the input and output impedance. This is output impedance. Output impedance. For finding output impedance, it is Vx by X with V in as 0, meaning that the input should not influence your circuit. So that's why you're making input equal to 0. In the input impedance measurement, you didn't connect this output because output should not load your circuit. So output should not draw any current. So that's why you're making open circuit. Load is made open circuit, and you put a Vx source here. Okay, this is how we can find these parameters. Now let us move on to find, okay, for the previous circuit what we had, at least we can find out what is R in, R out. Let me just take the previous circuit what we have discussed. Yes, we have discussed this circuit, which is, so just for purpose here. So what is R in now? The input impedance, of course, we wrote it as it is 100k in parallel with 200k. Of course, if you can just find out, it will become 66.66 kilo ohms is your R in. So this is R in. The R out happens to be 1k. The R out is RD. The R out happens to be 1 kilo ohm for this particular amplifier. Okay, it is as simple as this. And of course, the gain of this, we actually found that the gain is actually -4. So these are the specifications of this this CS amplifier. Okay, maybe we'll just do a few more circuits to find what is R in, R out. So let us take this circuit here. This is again a CS amplifier. This is VDD, RD, RG, CC, Vin, ground, source, drain. This is V0. What is the small signal equivalent circuit of this? Small signal equivalent circuit will look like this is Vin, and this RG will actually come here. This is RG, and we have, this is gate, source. Between drain and source, I will have GM into VGS, and this is RD. This is V0. This is Vin plus minus VGS. So what is the value of RG? Sorry, Rin. Rin is equal to RG. Rin is equal to RG. What is, this is RD. What is R out? R out is equal to RD. Of course, AV is nothing but minus GM into RD. So whatever value of RG you put, that will be the input impedance. Whatever is the value of RD, that is your output impedance. Fine. So this is one circuit, and suppose if I write another circuit which is slightly like this. So this is let me write this is VDD grounded and this is V0, and let me connect. This is CC, this is now RG, this is RD, and this is V0, this is Vn. So now how does the circuit will look like? The circuit will look like this. This is gate and this is source, this is plus minus VGS, this is Vin. You have a RG connected between drain and gate. So this is GM VGS, there is a RD connected here, this is RD, this is V0, and this is RG, correct? This is gate. So now what is the input impedance? Input impedance is looking into this, but this is a resistance not between gate and source, it is actually between gate and drain. So as we saw in the Miller's theorem, I should split this and write one resistance R1 here or some Rx here and other resistance Ry here. Then can this circuit or does this circuit reduce to something like this now? So this is now Rx and this is now gate, this is now, this is Ry, and this is actually Rd. This is V0, this is GM into VGS, this is Vin, this is ground. So if we can see in the Miller's theorem, we actually discussed Miller's theorem in the previous video. If you actually see what is Miller's theorem says, what does Miller's theorem says? In our Miller's theorem, we discussed the same similar type of circuit. Whenever there is an impedance is between two plots, so we got the expression for Z1 and Z2. So what was the expression of Z1 and Z2? So in case we have test, so what is Rx? Rx is like, okay, Z1, was it not equal to, this is like your R1, is it not Rg divided by 1 minus AV, where okay 1 minus AV is actually negative, then this becomes 1 plus AV. Then what is Ry? Ry is equal to Rg divided by 1 plus 1 over AV. Let me write it 1 plus itself. So now see this whatever Rx is now equal to Rg divided by 1 plus AV. So what is AV here? So AV in this case is equal to minus GM into. So what is the gain of the amplifier? So if you can actually see the gain of the amplifier, so gain of the amplifier is Ry into, it is Ry in parallel with Rd. So this is the value of gain of the amplifier. So what is Ry now? So Ry, you can, of course, you can actually take an example and then, okay, to just get an expression for, of course, we'll solve problems and try to get the numeric values of Rx and Ry. But here Rx and Rys are depending on what is the value of Rg and AV. AV is nothing but gain of this amplifier. So now what is Rin? Rin is Rx, which is nothing but Rg by 1 plus AV, 1 plus AV magnitude. What is Rin? Sorry, what is Rout? Rout is actually Rd in parallel with Ry. Rd in parallel with Ry, where Ry is Rg divided by 1 plus 1 over Rv. So this is what is the input impedance, output impedance and gain of the amplifier if you have a resistor Rg between gate and drain. Okay, we'll actually solve few problems on this so that you can quantify what is the value of gain of this amplifier and all those stuff. Okay, this is about the input and output impedance of the amplifier. And coming to what should be the value of input and output impedances, so it certainly depends on okay, let me just take up that example and try to find out what is input and output impedance of the amplifier. So for which I should know, okay, where is that sheet? So that sheet is here. If you can see here, one second. When we actually saw the input impedance of the amplifier, I'm just looking for that specific sheet so that I can start from there and then talk about the impedances. Okay. It's here. Okay, this is the thing what I was looking for. Now the question is, what is the typical input impedance that you expect? Because this is the input voltage that will be coming to the amplifier. So where is the input? Where is the source for this? The source for this is actually coming somewhere here from the external source. So this is actually Vs, and this will have an associated resistance R signal. So if this entire Vs has to reach here, there will be some drop here. So the drop depends on how much is the current that may flow here. So what is this V in now? Can I write the V in expression? So can I write the V in expression as equal to Vs multiplied by Rin by R signal plus Rin. So this is the input voltage that will reach the amplifier with a source signal of Vs and source associated resistance as R signal. So what should actually happen is, I should get the entire Vs should reach here. So when this V in is equal to Vs, so there are two cases where it is possible. Suppose the condition what we are looking at here is my Vs, my V in should be equal to Vs. That is, V in should be equal to Vs. So that is possible if there is no current. If there is no current flowing to this, if the current is equal to 0, if this current is equal to 0, then there is no drop. So when does this current become 0? This current becomes 0 when R in is infinite. If it is infinite, then this will go off, and then you end up with what? So when it is infinite, this is what? So this is 0. When this is 0, the entire current becomes 0. When entire current becomes 0, there is no drop. When there is no drop, whatever is this Vs, it will want to reach here. So this is one of the conditions. So when R in is equal to infinity, no current, so no drop, the entire voltage will reach here. So when this is infinite, this is negligible. This you cannot consider. So this entire thing will go with this. So V in is equal to Vs. What is the other possibility? Other possibility of getting V in is equal to Vs is, in spite of this current not equal to 0, even though if you are having some current, if this R signal becomes 0, suppose if this R signal itself becomes 0, so then this is 0, so then it is R in by R in will cancel out. So you will have Vin is equal to Vs. So when R signal is equal to 0, the entire source voltage will reach the amplifier. So what do you mean by R signal 0? R signal 0 means it's an ideal source, which you cannot expect the source to be ideal. So what is the other possibility? The input impedance should be infinite. So this is in your hand. This is in your hand. When you're designing, you can make this as high as possible. If it is infinity, it is the ideal case. So this is not possible to make it infinity. So a ideal amplifier is one. It should have an input impedance of infinite. Then what is the typical amplifier? So typical amplifier is one which will have its Rin. Its Rin should be as high as possible. As high as possible. So what we say is for a typical case, you should have input impedance very large. Input impedance should be very large so that the input voltage of the amplifier is approximately equal to the source signal that is being used here. So entire thing will reach here. So that's what is input impedance. How about output impedance? So you know that when it is open circuit, current equal to zero. So whatever is the voltage, the same voltage will reach here because there is no drop. But when you connect some resistor RL, can you see out of this gain times the input voltage, because of this R out, will you have some drop here? Because current is no more zero, because you have connected a resistor, this starts flowing. You cannot make this equal to zero. So now what is V naught is equal to? So can we write the expression for V naught over here? So is V naught is equal to AV times V in, of course minus AV times V in, into RL by RL plus R out. This is the expression of output voltage V naught, with this as the input voltage, and R out and RL. So when does this V naught is equal to this AV times V in? That is possible if RL is infinity, which is ruled out. So one of the condition is RL should be infinite to have this output equal to gain times input. So this is ruled out because you cannot have infinite load resistance, because you are supposed to draw some current. So what is the other possibility? The other possibility is R out should be equal to 0. If it is equal to 0, irrespective of the amount of current drawn by this, if you don't have anything here, any resistor, then there is no drop. Entire thing will appear here. So R out equal to 0 is the ideal amplifier. What is typically? So typically R out should be very small. So that V naught is equal to magnitude of AV times input voltage. So that's what the thing is. So Rin should be large, the input impedance should be large, output impedance should be very small, so that output is equal to output is input times the gain, or gain times the input. And in this case, to make the entire input voltage reach the amplifier, entire the source voltage reach the amplifier, Rin should be large. So now we found that in case of an amplifier, input impedance should be large, output impedance should be least. So that's what you learned in your basic courses. So input impedance of an amplifier should be as high as possible, and output impedance should be as small as possible. So we shall take up some examples in the next video and try to figure out what is R in, R out and gain of the amplifier in different cases.